Hi students, this is the last topic in OR. Fundamental theorem of duality. See the statement. If the primal or the dual LPP has a finite optimum solution, then the other LPP also has a finite optimum solution. And the optimum values of the objective function of the two LPPs are equal. That is, maximize Zx equals to minimize Zw. This is the maximize Zx of primal LPP. This is the minimize ZW of dual LPP. If the primal or the dual LPP has a finite optimum solution, suppose if you are taking primal of the optimal solution, you can prove dual of the optimum solution. If the dual of the optimum solution, then you have to prove that the other is primal of the LPP has also. So if the primal LPP has a finite optimum solution, then the dual LPP has also a finite optimum solution. Along with that, and the optimum values of the objective function of the two LPPs are equal. That is, maximize Z equals to minimize ZW. And see the proof. Let us consider the primal LPP B. So already you know that definition of LPP, definition of duality, and conversion of primal to dual. Let us consider the primal LPP B. Maximize Zx equals to Cx and subject to the constraints are Ax less than or equals to B and non-negativity restrictions x greater than or equals to 0. This is the primal LPP. Then the dual LPP will be here maximize Zx. So here you will get minimize Zw equals to B transpose W subject to the constraint A transpose W, which is greater than or equals to, here you got less than or equal, so you will make it greater than or equals to C transpose and W greater than or equals to 0. Let us assume that the primal LPP has a finite. We are assuming that, what we are assuming that if primal LPP has a finite optimum solution, then what you have to prove that dual LPP also has a finite optimum solution. So for that we are taking xb equals to B inverse B, then the corresponding value of the objective function of the primal LPP is given by Zx equals to Cx. So in the place of Cx you are taking the solution whenever, for example, if you are taking in the table of the simplex table, so basis in the matrix means you can take in the place of C equals to CB, in the place of X equals to XB. But already you take a condition, that condition is XB equals to B inverse B. In the place of XB, you can write by using this relation, in the place of XB you can write B inverse B. Now apply the condition of optimality to the primal LPP. Then we have, what is the optimality? Means Zj minus Cj. So these are the net evaluations, or by using, by calculating the net evaluations, we are using the delta J minus Zj, which is greater than or equals to 0. So but Zj is nothing but how, what is the Zj? Cb Yj minus Cj, which is greater than or equals to 0. So what is Yj? Cb inverse Yj equals to B inverse A. In the place of Yj you can substitute Cb into B inverse A minus Cj. In the place of Cj you are taking C greater than or equals to 0. So that same thing you are expressing here itself, which is greater than, in matrix form. Wherever you are expressing in the matrix form, we can express in this way. It can be further divided into two matrices as Zj minus Cj. So already here you have Zj minus Cj. So Zj minus Cj equals to, so what is the Zj? Zj equals to Cb Yj. Same thing you are expressing here also, Cb Yj minus Cj. So what you are writing here, that it can be further divided into two matrices. That is, these are the two different matrices. Cb B inverse Aj minus Cj for all Aj belongs to A matrix. Cb B inverse Ej minus 0 for all Ej belongs to I. So in simplex method we are expressing Ax equals to B. A is the original matrix. Then after adding either slack or surplus variables, for example in simplex method we are always adding the slack variables, so then we will get the identity matrix 1 0 0 1, that is nothing but I. So Cb B inverse Ej minus 0 for all Ej belongs to I. For the vectors in the basis, the costs are zeros. So that is Cb B inverse A minus C greater than or equals to 0. From this we can take this minus C, that side it becomes positive. So Cb B inverse A, which is greater than or equals to C, and Cb B inverse I. This is according to original matrix A. This is according to identity matrix So that's why CB B inverse I, which is greater than or equal to 0. So this is the identity matrix. So 0 by, it's a matrix. So 0 by I means 1 0 0 1. So anyway it becomes 0. That's why CB B inverse, which is greater than or equal to 0. Consider the transpose on both sides. Whatever you got here, by mistake I wrote this. After this you have to write. I put the arrow mark. But after continuation of CB B inverse A, you have to consider transpose on both sides. Then what is here? CB B inverse A whole transpose, which is greater than or equal to C whole transpose, and also CB B inverse whole transpose, which is greater than or equal to 0. So then apply transpose for all the terms. A transpose, B inverse transpose, CB transpose is greater than C transpose. So but A transpose, B inverse we no need to apply transpose. CB transpose, which is greater than C transpose, and here also B inverse transpose means you can get only B inverse. CB transpose is greater than or equal to 0. Now you can write C power T, as C power T is a right hand side. It's a right hand side vector of the dual LPP. About C power T we are telling, and also B inverse CB whole transpose will be the optimum solution of the dual LP. Let it be you are taking B inverse CB whole transpose, we are assuming the WB. So wherever B inverse CB transpose is available, we can write WB. Here that is available, B inverse CB transpose. Then A transpose into BWB, which is greater than or equal to C transpose, and here also B inverse CB whole transpose, then WB. So this means WB is a feasible solution. What is the feasible solution? Whenever if a solution satisfies both the constraints and non-negativity restriction, then it is called feasible solution. So this means WB is a feasible solution. Why it is a feasible solution? Since WB is satisfying the constraints of the dual LPP and also non-negativity restriction. This is the non-negativity restriction. This is the subject to the constraints. So these two are satisfying. That's why WB is a feasible region. Now the corresponding objective function of the dual LPP is, so this is the primal. From primal you are getting the dual. Now the corresponding objective function of the dual LPP is minimize JW equals to B transpose W, according to the whatever in the taking in the beginning. Same thing you are writing B transpose WB, means whenever you are writing W suffix B, otherwise CB in the place of CX, CB, XB means that is in the matrix, that is in the basis of the matrix. So B transpose WB, so that implies WB transpose into B. The next step. But what is WB? So we are applying transpose here. So then WB whole transpose whole transpose means you will get the same value B. The next step, what is WB? Already you wrote WB is the B inverse CB whole transpose, but here whole transpose. So again put the brackets whole transpose into B. So B inverse whole transpose, segregate means separately you are writing CB transpose whole transpose, B inverse whole transpose into B. So CB transpose whole double transpose means you will get the same value. B inverse into no need to apply transpose. So CB B inverse B. So but what is B inverse B? B inverse B equals to XB. So in the place of B inverse B you can write CB XB. CB XB is nothing but CX. You can write CB XB is nothing but CX. So CX means maximize ZX. So therefore we consider minimum ZW. What we proved that maximum ZX. So finally you can write if X is an optimum solution to the primal LPP, then there exists a feasible solution W to the dual LPP such that CX equals to B transpose W. What is CX? CX is maximize ZX, and what is B transpose W is minimize. Here there is a mistake, that's why I am writing in my notebook minimize B ZW means B transpose W. Therefore W is an optimum solution of dual LPP. Similarly we can prove starting with W to the dual. Suppose here we assume that we are taking primal LPP, so we proved that dual LPP. Suppose you can consider dual LPP. If you take dual LPP you have to prove that primal LPP. Here if the primal or dual has an optimum solution, then the other LPP also has a finite optimum solution and their optimal values are equal. Optimal values means, optimum means either maximum or minimum values are equal.